All right, let's get rocking with the question: why zero trust must be under zero knowledge? That probably doesn't mean a whole lot to most of you, unless those of you who have heard me blabber about zero trust under zero knowledge, obviously. But assuming most of you have not, let's dive in with a bit of context. So here, digital business is truly at a crossroads. It's like, why, you might ask? Well, on the one hand, digital transformations are driving revenue, right? So we IDC, digitally transformed organizations, produce more than half of global gross domestic product. That's a lot. So digital transformation, digital business is definitely, ever more growing, ever more present, and will continue to be, and will continue to grow, probably even faster. My fun prediction is that within 5 to 10 years, there will not be any more software developers, because generative AI will have taken over. On the other hand, digitization is also driving exponential risk, right? We're, the yin and the yang, the good and the bad. That's exactly what we have here. Cybercrime will cause 10.5 trillion in damage by 2025. Almost 10% of the projected 2025 global GDP, with an annual and accelerating growth rate of 15%. So it's not growing at a steady rate, it's accelerating, which is not too surprising. Like, fun fact, ChatGPT is already being used in cyber hacks, successfully, I might add. So what else is happening? Well, and regulatory compliance is further complicating the matter. Why? Because nation states mandate more stringent security frameworks. Given that you have 10% of projected global GDP going up in flames because of cybercrime, not fun. Therefore, more and more stringent security frameworks are mandated. In the U.S., this is the zero trust order, as it's being called. In other nation states in the EU, it's called differently, but basically, it means that every organization that wants to do business with the government, or is doing business with a business that is doing business with the government, must implement these type of significantly enhanced cybersecurity frameworks. Data privacy regulatory enforcement is also on the increase in Europe. If you care to look at the docket of the EU court, you see cases piling up, and they are, in fact, a large part is concerned of that docket is now concerned with data privacy lawsuits, and they're crossing jurisdictional boundaries. How so? Well, in Europe, if you're a US or a Japanese or a Korean, or a Chilean or a Tanzanian company doing business with an EU company, and you're receiving private data from them, not private from a business point of view, but for example, you're sharing customer data. And that company in the EU is getting fined. Newsflash. So do you. Why? Because you didn't ensure that the business is handling the private data which you received according to GDPR. The courts don't care. Your responsibility. You're taking data from EU citizens. You must ensure it's handled properly. And you must ensure that it was handled properly before you received it. You don't do it, tough luck. You're up for up to 4% of revenue for every single infraction. So, what other, in other bad news, we have new privacy laws popping up everywhere. After California took the lead in 2020, we have now 5 US states. They created GDPR-like laws in 2022, and that trend is going to accelerate. You have, that's not only in the US, everywhere, the data privacy regulatory frameworks are being tightened. So if you're a business and you have a lot of digital business, even if you're shipping stuff, physical stuff, it's still digital, newsflash, and you don't get your act together, you're going to go out of business faster than you think. So things enterprises must do, and soon. You have to decentralize enterprise networks into smaller subnetworks to be able to prioritize security and performance, because again, you cannot have both. You can have things that are fully decentralized, so you have many endpoints, many devices, everybody interacting with you, and think that you'll be able to keep a network of that size secure and performant. It's just not possible. Why? Well, the underlying reason it's called the CAP theorem: consistency, availability, and partition tolerance. If you don't know what that is, look it up. It's one of the fundamental things in computer science, and you can't cheat that, which means business can't cheat that either. So you need to make choices. Only 2 of the 3 you can have. You can decentralize, and you can have security, see Bitcoin, but you can't have performance, see Bitcoin. So what else? You need to, because you want zero trust, you need to authenticate and authorize every other participant for every single digital business interaction at all times. So even if you just did business a second ago, no. You need to assume that entity that's trying to connect with you is compromised. Even though a second ago you established it was okay, everything's shiny. Next interaction, you must assume it's adversarial. So you need to then also prove and verify the authenticity, integrity, and correctness of every digital service transaction and its associated supply chain of prior digital transactions, informing and triggering that digital service transaction. What does that mean? That means, in the simplest form, you give me an order, you need to prove to me that the order is actually correct, that the data in the order is correct. So not only that you're sending me the data, but that the data that you're using is actually correct, that the data between the two of us is properly synchronized. That's a simple example, right? Much more important one is when you establish a security service between an enterprise network and an enterprise laptop using, for example, a telecom SASE service from a third-party provider. Oops. So everybody now, you have now 3 parties in the mix, and all of them need to prove to each other that A, that they're authentic, and then B, that the data being exchanged is authentic, has integrity, is correct, and where the data came from is also correct. No one does that right now. No one. If you say you do, you're diluting yourself. You can't, because for that you need a few other things that we'll talk about. And because of our data privacy regulatory enforcement actions, you need to minimize the exchange of sensitive data in digital service transactions, and ideally to zero. So you're not only need to prove that everything's correct, authentic, has integrity along the entire digital supply chain, but you also shouldn't exchange anything, which sounds like paradoxical, but that can be done. So because if you exchange data, A, it's typically business sensitive, and B, you have there might be PII involved, which you don't want to. So you want to derive statements from that data that you can prove to others without revealing that data. If that sounds like zero knowledge, yes, you're right. That is, and we'll talk about that in a second. So what can you cast this under, right? So all of these four things put together is, you could call multi-party zero trust under zero knowledge, or MZTZK. Yet another TLA. But this one is, I think, going to be foundational for the future. Multi-party zero trust under zero knowledge. Right. Now, what is actually zero trust? So this is the definition from NIST. So it's kind of operative definition of zero trust. And zero trust architecture is that zero trust provides a collection of concepts and ideas, note concepts and ideas, designed to minimize uncertainty and enforcing accurate and least privilege per request access decisions in information systems and services in the face of a network viewed as compromised. So every time someone wants to connect to you, you need to assume that that network is compromised. And a zero trust architecture is an enterprise's cybersecurity plan. Notice plan, zero trust before, concept and idea. Now here it's a cybersecurity plan that utilizes zero trust concepts and encompasses component relationships, workflow planning, and access policies. Okay, means a lot and nothing. Therefore, a zero trust enterprise is the network infrastructure, both physical and virtual, and operational policies that are in place for an enterprise as a product of a zero trust architecture plan. Again, plan. This is wonderful, but they just, it's like, are making a lot of tech consultants very rich for producing those plans without actually improving security. That means, of course, that doesn't mean or say a whole lot, right? The proof is in the pudding. If you're not actually doing stuff, right, that is actually zero trust, and there's actually a zero trust architecture, physically implemented, provably so, it doesn't mean anything. So federal government is struggling with that. Businesses doing business with the federal government is struggling. So now we know what zero trust is, kinda. Let's move over to zero knowledge, right? So zero knowledge definition is, if a statement is true, like I am over 21, no verifier of the statement learns anything other than the fact that the statement is true. I'm over 21. In other words, just knowing the statement, I'm over 21. Now, the actual secret, my birth date, is sufficient to construct a scenario that shows that the prover knows the secret. So what's a good example? An intuitive example is Alibaba's cave, right? So Jimmy tells David, says to Jimmy, dude, I know the secret password to Alibaba's cave. And Jimmy says, no, you don't. David goes, yes, I do. Jimmy goes, then walk in path A, come back out path B, because in between is Alibaba's cave, so you need to open it up to be able to come out of it. And David says, okay. So David goes in path A, gets to the door, whispers the password secret. The door opens, he walks through, and comes out on the other side. And now Jimmy knows that David knows the secret without David having to reveal the secret. So Jimmy is suitably impressed. This is what you call an interactive zero knowledge proof. There is another form of a zero knowledge proof, because imagine you have to do this like over a network, and it's not as simple. You would have to. There are scenarios where you have to basically repeat that exercise many times, because you have more than two states, 0 or 1. There is business logic that's more complex that needs to be provided. So you have multiple input values. So you would have to run through millions or billions of possibilities. That's obviously not going to happen and not efficient. So what do you do? So David simulates all these outcomes through a random generator, and produces and then collates all these simulations and commits to them in a cryptographic manner and presents them to Jimmy, and then Jimmy can verify that through all the billion attempts David proved the same outcome. It's like, okay, great. So then that's what's called a non-interactive proof, because David sort of like does all the work for Jimmy through basically randomized execution of business logic that proves the secret. And that's then packaged all together and given in one short proof to Jimmy. And that's what's called a non-interactive zero knowledge proof. All right. Now, the big question is how to get it done. The simple question is build on, that's obviously complex, but simplistically saying build on and integrate with the Citopia and the ITN networks. Right? It's like, wait, what? Hold on. So why? Because they are what? They're decentralized federated network built around the concepts of self-sovereign identity, which is a zero trust enabler, and based on accepted global standards and the reputation of more than a dozen global enterprises. So the ITN integrates, has zero trust, builds in zero trust architecture, so you can build on that. So Citopia is built in data privacy, and ITN also, because it doesn't utilize any PII whatsoever, has built-in data privacy, right? So both networks have built-in data privacy. All PII data and data exchanges is under the owner's control with built-in zero-knowledge technologies, and that's particularly on the Citopia side. We have implemented that and shown how that works in the mass multimodal pilot, as well as in the Vintrack pilot that we just demoed. All of this will be open sourced at launch, and therefore guarantees no vendor lock-in, which is also important. There is no single entity, because both networks have corporate governance structure that prevents control by a single or even few entities. So these are foundational elements that you can utilize to implement a zero trust under zero knowledge architecture. So let's take a look under the hood a little bit. It's like, how is that actually achieved? So you have independent networks working together to create value, right? You have we have Citopia as a layer 3, an application network. We have a layer 2, that's the ITN, and we have a layer 1, which are actually the blockchain protocols upon which the ITN and soon also Citopia will rest. We have, so each of them provide value to the one above, right? So ITN inherits the security properties of the underlying layer 1 blockchain, and that is then that is packaged into certain functionality, in this case, decentralized identifiers and verifiable credentials, and they can then be utilized up here in Citopia, where you add additional zero knowledge capabilities, because down here this is basically, or it is zero knowledge, because there's no PII involved, and you don't know anything unless you do very, very sophisticated analytics. But again, if you can decorrelate between the layers, which is done, then again, you can observe things on layer 1 that doesn't tell you anything about layer 2, what's going on there. The same thing is between layer 3 and layer 2. So they're both built on Web Consortium Decentralized Identifier and Verifiable Credential standards, and they're using zero knowledge proofs, which we're basically packaging. So David's proof in zero knowledge to Jimmy that he knows Alibaba's cave's password is packaged into a verifiable credential, where that is then issued, right? In this case, David issues it through a Citopia self-sovereign digital twin, which is an abstraction layer that operates between Citopia and the ITN, and within Citopia between different Citopia nodes and between different ITN nodes as well. So that is issued in zero knowledge to the holder, Jimmy, right? Countersigns the credential. There's what is written here are into the DID registry. Those are only the DIDs, not the credentials themselves. They're exchanged between issuer, holder, and then verifier, because Jimmy tells me, hey, David really knows the secret to Alibaba's cave and secret password to Alibaba's cave. And I go like, no. It's like, yes, here's the proof. No. It's like, yes, here you go. So Jimmy presents, David's self-issued verifiable credential in a verifiable presentation to me, so I can verify that presentation came from Jimmy, and I can verify that it was issued by David, and that I can also then verify the proof. So that all happens in Citopia. ITN provides only the registry of the decentralized identifiers that are used to establish authenticity and integrity of the identities used within Citopia. So you have a decentralized network ecosystem nodes, and each node has all copies of the DITs. That's the ITN. So what does that overall, in a bit more detail, what does the Zero Trust Web3 solution architecture look like? So we increase security as we go down all the way down to layer 1, because that's the most secure piece of everything. There's nothing more secure than the Bitcoin or the Ethereum blockchain. They have been fully open, 100% available, and has never been compromised, even though they have been fully open and everybody can participate at any time, ever. And Bitcoin has been now around for 14 years, and Ethereum now for nearly 8. And people who have written code utilizing those networks have screwed up, but the networks themselves have never been compromised. So this is the most secure. That's the security anchor. As we go up the stack, privacy as well as speed and obviously control goes up, because this is the most decentralized piece of the stack. That's the current Web3 world. Then we have the integrated trust network as a federated global identity services. Then within these blocks that are Citopia, you have a zero-knowledge execution and processing network connected to a middleware layer, which is basically sitting on an application abstraction layer. And these 3 layers are basically what is Citopia, or Citopia node, and multi-party applications that are built can be integrated in this Citopia node architecture that can then therefore effectively utilize zero-knowledge execution and processing, and can utilize the integrated trust network while also enjoying the security of Web3 blockchain protocols, provided that whatever application that was coded up here doesn't have bugs, right? That's always given. So this is the high level view into something that even if you wanted to build separately, this is a high level architecture that is zero trust under zero knowledge, that can be utilized by for multi-party coordination, multi-party business processes. All right, now let's go one level deeper, right? So we had these layers. How does that actually look? It's how does Citopia and the ITN actually work together? Well, you have the ITN nodes down here with their self-sovereign digital twin and the ITN core services that operate that are there for DIT management, creation, updates, reading, and archiving / deleting of or inactivating of DITs. These services that ITN provides, again, are then accessed from various Citopia nodes, such as a mobility node, through the nodes SSDTs that act as a service for applications from like a parts supplier or electric vehicle owners that are operating on that particular Citopia node. However, the EV owner might also want to have car insurance. Well, the service providers on the Citopia node, you have EV charge service and insurance services that are operating applications here. So the EV owner from this node can discover the EV charging service and the insurance service application running on this particular node. and can then access via the Citopia node the applications here. So that is a this way, so it's a loosely coupled network. There is nothing like a consensus algorithm or anything like that. It is this is based because there's nothing except the Citopia membership credentials. Nothing else is basically being replicated between the different nodes. So the Citopia node basically acts as a wrapper around the applications of power suppliers, insurance services, EV charge services, base station services, in the telecom side and telecom services, and they are all interacting with one another on demand, leveraging the ITN DIDs for security and being able to enable zero trust, while Citopia offers zero knowledge capabilities that can be integrated into the applications that are running on the various Citopia nodes. So to wrap it up, what do we have? 4 points to keep in mind. Digital business is at a crossroads. Security and compliance costs grow exponentially. Not bueno. Enterprises must decentralize their trust boundaries. In other words, grant autonomy. Oh my God, shock. To be able to focus on security and performance. Right? So you can't beat decentralization. So join it and grant more autonomy to your networks at the edge. In fact, there is no centralized network, shouldn't be anymore. It should all be, trust networks that are working in coordination with one another, very similar to what Citopia is doing. Which brings me to the next point. Enterprises must implement multi-party zero trust networks under zero knowledge, MZTZK. And, as I showed you, ITN and Citopia have built in zero trust and zero knowledge. So building and migrating business onto these networks basically gets you compliance without having to break the bank. The punchline here is ITN and Citopia can help enterprises achieve multi-party zero trust under zero knowledge. And with that, I stop and open up for questions.
Thank you, Andreas. I see we have 3 questions so far in the chat. So let's start with the question first from Pramita. If how VC's work is inherently ZK, then what does the ZK layer in Citopia do? Is it more of a verification that ZK is actually being preserved?
Yes. So in quote unquote traditional VCs, you just verify integrity through the digital signature and authenticity by being able to verify the signatures over the issuer from the issuers. Here in Citopia, when we add zero knowledge to verifiable credentials, you're adding a second verification step. Right now, you're verifying that whatever is presented to you is correct, and without you having to worry about looking at or looking at and storing, preserving personal identifiable information, for example, or business sensitive information from another company. Again, as soon as you hold that, you're responsible for it. Your costs go up then because it has to be secured. You have to prove that it's secure, et cetera, et cetera. So in this case, you know, it's like I would like to say, ignorance is bliss, because you only know what you need to know and nothing more. And the zero knowledge proof verifies that everything is correct. Did that answer your question?
I'm still a little confused, but maybe we could take it offline. I noticed that there are other questions on the chat.
Yeah, we can come back to it. And I would really like to understand what you're still confused about. And we do have 20 minutes. So
Okay.
so let's take the next one and come back to you if we have time at the end. Next one.
Sure. Interaction between digital twin is zero trust, but if the digital twin is accessed by API, is it still zero trust network?
Yes, it is. The self-sovereign digital twin is an application that is part of a Citopia node, right? So every entity in the Citopia network has an SSDT. Therefore, they can integrate that into their applications that they want, so that they can communicate with other entities within the Citopia network and the ITN if they want to. So this is an abstraction, integration, and translation layer that we have built, and that is only controlled, and only the owner and controller of that self-sovereign digital twin actually can see what's going on inside of it. Did that answer the question? I guess silence means yes. Shall we go on to the next one?
Sure. What is the difference between the Citopia nodes being connected using Citopia API versus the Citopia nodes being connected via ITN?
Very good question. They are both using, so Citopia nodes communicating with one another, they're using the SSDT of the node, of each node. And a Citopia node is also using that very same SSDT to communicate with the ITN, because each ITN node has a self-sovereign digital twin that another self-sovereign digital twin connects to. Just there are different services available, right? So you have basically a base self-sovereign digital twin, which is the one that's provided by the ITN, and then Citopia is adding more and more capabilities, more services to a Citopia node self-sovereign digital twin. Each Citopia application can utilize, and if they want to add to the Citopia self-sovereign digital twin, so their application that they're building can leverage the Citopia nodes capabilities, and they can build additional capabilities that they want and that they want to expose to other applications on the Citopia network. Right, so it's basically a service menu. You have the service menu of the ITN, you have the service menu of Citopia, and then you can add items to that service menu that is specific to that application, that other applications that also have service menus can utilize.
Can I ask a clarification question?
Sure.
So is it correct to assume then that in cases where Citopia SSDT is leveraging the core services, the connectivity between two Citopia nodes is through ITN, right? And where there are those extra services you're talking about, then the connection between two Citopia SSDTs are direct. I mean, direct using the Citopia API. So sometimes ITN APIs are being used if we're leveraging a core service, versus sometimes Citopia API is being used if it is not a core service.
That is correct. You, as I said, you have a service menu that has basically 3 sections, right? You have your appetizers. Those are the ITN services. Then you have your main course, which are the Citopia services, main courses. And then you have your dessert. Those are your application-specific services that have been built into your very own Citopia SSDT. So Citopia SSDT basically has the appetizers and the main courses, and then you add, if you want to, dessert to it.
Okay. So as a mobility service provider, then, and if I'm leveraging Citopia, then am I running 2 different SSDTs in the network?
No. If you're an application provider, you only run the SSDT or replicas of your SSDT in one or more Citopia nodes, right?
Okay.
That's it. If you're an Citopia application provider and a Citopia node operator, then you run the SSDTs for your application, and because you run the Citopia node, you also run the SSDT for the Citopia node, right? So we're treating every application as its own entity, that is including Citopia and each Citopia node and each ITN node. So and basically the SSDTs give you options of how to interact with each member of that ensemble of ITN nodes, Citopia nodes, and Citopia applications.
Okay.
Right. So that implements the principle of building as small a network as you want, or that is, has the right security properties and the right performance properties that you want. Cool. Parth, next question.
Sure. When do these Citopia nodes communicate with one another? Is it strictly for peer-to-peer communication, such as proof presentations?
So yes. It is strictly for peer-to-peer communication, but it is also there when you are trying to access services, right? So when you're trying to access service, right, from one Citopia node, right? Let's say your part supplier service also wants to offer an EV charging service on their property, right? So then the EV owner connects to the part supplier application, and the part supplier application and the SSDT then knows where the EV charging services application is on the other Citopia node, because it can discover it through the Citopia node service menu. Oh, there are other Citopia nodes, and they have these types of services available. Oh, I want to use that EV charging service. So then the part supplier SSDT connects through the through the Citopia node that holds the EV charging application, SSDT. So you're going from application on Citopia node mobility, connect to first the Citopia node of the EV charging service, right? Because you need to make sure that Citopia node is just not letting anybody in. You just have to you have to prove that you're actually a Citopia member. That's your first layer of security. Then it routes that request to the actual application, right? So the Citopia node is a security traffic cop with all the incoming traffic, and then it hits the SSDT of the EV charging service application, and that request then is authenticated in the application to make sure, yes, that request is actually okay because the part supplier registered before offering that EV charging service with the EV charging service, and they're now a customer. So, and that goes for every single interaction. The Citopia node is a security traffic cop, basically, and that makes sure that everybody who requests something is authenticated and can prove that they are a Citopia member through the Citopia membership certificate. Does it make sense?
Yeah, thank you.
Parth,
Right.
any new
Yes.
questions? Okay.
Yes, two more questions. I think peer-to-peer communication, which is including write transaction, is slow. What is the tech in order to speed up the communication?
Yes. So writing is slow if your all communication is async. So yes, we're routing, but we're not routing to like unknown participants. It's not like in a true peer-to-peer network where the source, right, the sender, does not know where the receiver of the message is, right? In that case, yes, you have to go through the message is sent from the originating node to the nodes that it knows and say, hey, do you know this guy? It's like, and if they do, then it's relatively fast because it's a direct connection. But if not, the message has to be forwarded and forwarded and forwarded until it finally reaches a node where that knows the recipient, right? That's why, like, true peer-to-peer, like where all the peers are not known, is much slower than if you know exactly where to go. And in Citopia, because we're using the DIDs and the service section in the DID document as basically a service menu. So the service menu of a Citopia node, which is known because everybody knows where all the nodes are, because they're replicating the new Citopia memberships to those nodes. They then offer and say, hey, I have these service providers, right? These endpoints available. And then any application can take that, can hit a specific service provider endpoint and get a listing of all the services that are available. So now I can directly integrate a Citopia application service in my Citopia application, and then it becomes basically as if I'm hitting an Azure or AWS service, right? Where think of the Citopia as the AWS cognito that then routes the request to the actual application, and that's pretty fast. So it's it will come down in the end to sizing your Citopia node and your application properly. And that is up to each Citopia node provider. How they want to size their node, how big their cluster is supposed to be, or how many clusters they want to operate, how many nodes they want to operate. Does that make sense? Cool. Parth.
Yes, next question is it correct to understand that interaction between Citopia API nodes is CT, as in zero trust, and interaction between Citopia application is zero trust, but interaction between Citopia API node and Citopia application node is not zero trust because that API interaction is not by zero trust, did to did?
No, the routing in the well, the routing of the request to access an application is that is not in zero trust because the application operates in the Citopia trust boundary. Right, it's on the same cluster, right? Where everything operates in the same in the same subnet, for which I've established a zero trust policy. What the application needs to do, it needs to authenticate the sender of the request, right? And then obviously you have the typical the typical cluster security policies that are going to be implemented with encrypted traffic and certificates that are being used and that are managed by the cluster, right? So that's a given, but there's a significantly higher level of trust within a Citopia node than outside of it, obviously.
Okay.
Hello. Thank you for answering the question. So you mean that the interaction between the API node and Citopia services interaction between the application node and between Citopia services API node is not by DID based API call, but it is regular API call in the same subnet. That is the reason why it is secure. Is that correct?
Yes, because it runs in the same, it runs in that same node architecture. So you're using within the node, you're using your typical inter-application security approach that is based on, you still use for example OAuth, but you're using OAuth and the tokens are DIDs, right? The identifiers are DIDs, and therefore since everything is signed, right? Everything's signed, so you're combining the best of both worlds. Right, because you still need to the originator of the request comes outside of the trust boundary, right? And even though the Citopia node authenticates the request as coming from a Citopia member, and is therefore thumbs up, the application needs to check whether that request is in line with the security policies of the application. So is it registered is that type of request allowed for this particular, user, right? So so while the Citopia node ensures that sort of like is you can think of this as the bouncer, at the entrance of a club, you still, as an application, have the right to refuse to club. You can refuse to talk to a person who wants to talk to you, right? So similarly, an application can refuse a request or accept a request if it meets the security policies of the application that is running on the Citopia node.
All right, thank you very much. And just one confirmation. So that means there are as many Citopia API services node as the Citopia application node. That means there are many numbers of Citopia.
Yes, there can be millions, hundreds of millions of different APIs that you can discover if you want to. You don't have to, right? You can just run an application on a Citopia node and not worry about any other services on any other Citopia nodes. But if you want to leverage their services that they have and not build it yourself, you can.
Okay, thank you very much. You've been very helpful. Thank you very much.
Excellent. We're a little over time, but that's okay. Parth, is there any more questions?
Yes,
There's
one last question. So which ensures CKPs, SSTTs by themselves or SSTTs with Citopia services or SSTT Citopia services interacting with core services?
Say the beginning of the question again.
Which
You were breaking up.
ensures CKPs?
Oh, the services of the Citopia node. So a Citopia application could choose not to use the zero knowledge proof services of a Citopia node and build it themselves, or not use it at all. But if they do, then yes, it can utilize zero knowledge capabilities of a Citopia node to add those capabilities to an application's services. That's the whole point. So you can offer services that are under zero knowledge. And in the next iteration, we're going to go more general so that you will have basically a general purpose execution framework that allows you to execute basically arbitrary business logic, and then provide the proper zero knowledge proof around the execution of that arbitrary knowledge. Think of it as, you're executing smart contracts, but you're getting a proof that the smart contract was correctly executed, but under zero knowledge. So you're getting a whole bunch, or you're getting a recursive proof over all the recursive proofs that are required to prove that a particular transaction was executed correctly. And that's what you call that was recently, and I talked about it a few times, so what's called a zero knowledge Ethereum virtual machine, or short ZK EVM.
Thank you, Andreas. Yeah, thank you.
All right. Well, we are at the top of hour. So thanks to Andreas for your presentation, and to the audience for taking the time to join us today, and look out for the recording on our website. Thank you, everyone.
Thank you.